All right. So good afternoon, everyone. So I'm Jayesh from the British Society for Geomorphology Postgraduate Forum. So we have Dr. Monika Devi. She's based in Romania, and she has been working on luminescence dating since like past 5-6 years. And she completed a PhD in luminescence dating based on her thesis, Multispectral Luminescence Studies, Methodological Developments and Applications from the Atomic, Molecular and Optical Physics Division, Physical Research Laboratory, Ahmedabad, India, with Dr. Naveen Chauhan. And she has been doing a postdoc now. And yeah, she is going to take us today with a very important topic, like how the traps, electron traps, which are trapped in, means which are like geological clocks, which are mechanisms, and how you can use them for dating for different purposes in geology, in earth sciences, and beyond, as well as in geomorphology. So thank you, Dr. Monica, for joining us today. The floor is yours. Please take it over.
Thank you. Thank you, Jayesh, for the introduction. Hello, everyone. First of all, I would like to thank British Society of Geomorphology for giving me opportunity to present my work. In the presentation, I'll be talking about how the tiny charges stored inside the crystal helps us to understand Earth's and human history, especially in Quaternary period. So I'll be talking about these glowing crystals today, how these crystals glow and how they store energy, and tells us about the past events. Okay, as you may all have seen these glowing toys and how these toys work. So in the daytime or under the light, they absorb energy, and when you take them in dark, they emit that absorbed energy and they glow. So similar principle is in charge trap dating also, but here we work at bigger scale where the energy is stored for millions to billions of years. So if we want to understand the mechanism, we can understand it with the band theory of solids. So here is the crystal. Yeah. So we know the crystals have some impurities and defects. So those impurities or defects creates metastable states within the forbidden gap of valence band and conduction band. And ionizing radiation, they creates electron and hole pair. Some of the electrons will be trapped in these metastable states. Now, depending upon the lifetime of this metastable state. For example, if they have very low lifetime in seconds to minutes, then they emit their light immediately. So this kind of phenomena we see in these glowing toys. So they store energy for few seconds, then they emit it, that we see in the dark light. However, in case of geological processes, we are interested in the traps which have lifetime of the order of millions of years, and they are deep traps. So what they will do, they will keep on accumulating energy from the ionizing radiations, and once we stimulate that energy from the external sources, we and this electron will recombine with hole and the light will be emitted, which is known as luminescence. And this luminescence intensity is proportional to the trapped charges over here, which is further proportional to the time since when this crystal is getting irradiated from the ionizing radiations. So this proportionality we use in trapped charge dating to calculate the time from past events. So mainly it tells that since when the crystal is getting exposed to radiations. Okay, and the energy of these stored charges is very low, of the order of 2 electron volt. If we use, if I am talking about geological traps, so this 2 electron volt is so that's why we have to always keep our sample in dark. Even daylight, visible light has energy of the order of 2 electron volts, so that can emit this stored charges. So we have to be very, very careful. We have to do all processes in the dark. And we use this stored energy in the controlled environments only. Okay, and more easily we can understand the concept of charge trap dating using the water beaker example. Let's suppose we have a beaker and water is falling in this with a constant drop rate. And if we know the water accumulated inside the beaker and the drop rate, we can find the time since when water drops are falling in the beaker. So similar concept is in geology. Here in geology, we mainly deal with quartz and feldspar minerals. And in nature, these minerals are surrounded by radioactive nuclides, uranium, thorium, potassium, and they emit alpha, beta, gamma. So these radiations ionize the crystal. And so what is happening in nature, consider this quartz and feldspar as beaker and these ionizing radiations as tap. So these ionizing radiations are depositing energy. So if we calculate the energy stored inside this mineral, quartz, feldspar, and the rate of energy deposition, we can calculate the time since when this quartz or feldspar is under the exposure of this ionizing radiation, which will be the time or burial time of this particular mineral. And our clock starts when this beaker is empty or when there is no signal in quartz and feldspar. After when the clock will start, our signal will start to build up. And for charge trap dating, we mainly used two techniques, luminescence and electron spin resonance spectroscopy. And let's go a bit into the history of these techniques, how these techniques have evolved. So the first observation of luminescence was made in 1660 by Robert Boyle, where he saw that diamond is glimmering when he kept the diamond with the warmth of his body. So heat from his body was stimulating the charges stored in the diamond and he was able to see the emitted light. So that was the first observation of luminescence. And after the invention of photomultiply tube, because the energy emitted is very weak, so we need to extract that energy, we need very sensitive equipments. So after the invention of photomultiply tube, its application in radiation dosimetry started, and in the year of 1950 to 1970, its application to date the heating events started, especially potteries or ceramic materials. But the major revolution in the field came in the year of 1985 when David Huntley uh, reported that the stored luminescence can be bleached with the daylight. So it opened up a new era of application where all the events in geology which have seen the light, for example, aeolian, glaciofluvial or fluvial, those all events can be dated using luminescence technique. So nowadays, luminescence technique is not only used for dating, it is also used to understand the Earth surface processes, which I'll be also talking about. And it is used in, I'll be talking about particularly geology and archaeology. And now about electron spin resonance spectroscopy. Electron spin resonance spectroscopy, it detects the paramagnetic centers, or we say free radicals, which have unpaired spins. So the first observation was made in 1944 by Professor Jayesh, where he detected the magnetic resonance from paramagnetic materials. And at the same time, there was rapid development in the Europe and particularly in the Oxford group led by Professor Bliney, where they used this ESR technique to study crystals and transition metals. And in the year of 1960 to 70, it was used in physics, chemistry, and biology to study the free radicals and molecular structures. And in 1975, Professor Akya, he introduced ESR dating for geological and archaeological materials. And nowadays it is used ESR everywhere, chemistry, biology, geology, and archaeology, and radiation dosimetry also. Where we detect, wherever we have unpaired electrons, we can use this technique. And on the right, you are seeing the first instrument developed by Professor Jayesh. Yeah, now let's talk about the concept of luminescence dating. As I mentioned, that crystal stores the energy in the traps, and we extract this stored energy in the controlled environment in lab. So this is the schematic of the TLOSL reader for luminescence. Here for stimulation, we have different sources. We can either stimulate with heat. Here you see there is heating plate, and we can stimulate it with light. There are different LEDs for stimulation, and for the detection of signal, we have photomultiplier tube. And for the irradiation in lab, we have beta source, which is strontium yttrium source. So this is the schematic. And when we stimulate the crystals with heat, so we see these peaks. These peaks corresponds to the each trapping center. And from these peaks, we can understand the dynamics of these traps. And if we stimulate the crystal with these LEDs, or we say optical lights, we observe this exponentially decaying signal. And these signals are used to calculate the doses stored in the minerals. So when I say dose is nothing, it's just energy per unit mass. Okay, so in luminescence community, this single aliquot regenerative dose protocol is widely used. So how this protocol works, once you extract the quartz and felds per mineral, first you extract the natural luminescence stored in the crystal, then in laboratory you give the doses from this beta source, and then you interpolate this natural luminescence with the laboratory dose luminescence, and you can calculate the dose stored in the crystal. And these crystals also have some limit to store the charges, which is defined as a saturation dose. Means this there are limited number of defects, and beyond that these defects can't store energy. So that defines the saturation limit of any protocol in luminescence dating. Now for electron spin resonance dating, here also we probe the trapped charges, but in case of luminescence, we were having signal from the recombination of electron and hole. But in case of electron spin resonance, we either probe the electrons or holes, trapped holes. So this also gives the same information. So how this works? So these electron and holes, and they have spin half. And when this material is placed in the presence of magnetic field, according to Zeeman effect, there will be splitting of the spin states. And we see then this broadening of the splitting will increase as we are increasing the magnetic field. And we are also sending microwave frequency at the same time. So when there will be resonance means when the splitting energy will be equal to the microwave energy, then this electron will absorb this microwave energy, and we will see a absorption dip. And this is the signal from particular defect present in the sample. And this signal, the intensity of this signal carries the information about the energy stored in the crystal and hence about the age. So in ESR, we apply magnetic field, it splits the spin states, then at resonance condition, it will absorb microwave, and we will see a ESR spectrum of different defects, or we say free radicals. Yeah, in case of dating for ESR, we use these two centers. First is aluminium hole center, and second is titanium lithium electron center. Here are the typical spectra of these two centers are shown. And we see that as we are increasing dose, the intensity of these signals are also increasing. Means if we will have more energy, there will be more electron holes stored, and we will have large signal. Okay, and to calculate the ESR intensities, we use these differences in the peak to peak amplitudes. And in ESR community, the multiple aliquot additive dose, which is also known as SMART protocol, is widely used. Here, how we calculate the dose. So we give doses. We make different aliquots, and then we give doses to each aliquot in the incremental order, and these are the ESR signal. Then we extrapolate this ESR signal to negative y-axis, and this intercept at negative y-axis is our dose stored in the crystal. So that's the methodology with ESR dating. Now this was about the dose. Now to calculate the age, we need dose rate also, means the rate at which energy is being deposited inside the crystal. And this is a just typical example of the field site is shown. That's how we take sample. These are the pipes where we collect sample. And here our crystals, quartz and feldspar, they are surrounded by radioactive nuclides such as uranium, thorium, potassium, and they are contributing to the dose rate. So we need to calculate their concentrations, that we do either with the alpha spectrometer or gamma spectroscopy. Yeah, and this is the typical peak for potassium is shown. That's how we calculate the concentration of these radioactive nuclides. And along with this, another important factors are the samples over here, they can also have some moisture content. And the presence of moisture, it attenuates the alpha, beta, gamma radiation significantly. So we need to be very careful with moisture content, and we need to calculate it. And in the dose rate, cosmic rays also contribute. So we also need to calculate the contribution from those cosmic rays. And along with this, there are this alpha, beta, gamma radiations. They have certain ranges in the sediment. So we need to consider these ranges also. So alpha has range 20 micrometer, beta 3 millimeter, gamma 30 centimeter. And now, depending upon the grain size that we are using, means availability of the material, if we are using coarse grain, then we can remove this alpha skin using hydrofluoric acid treatment. Then we can avoid the contribution from alpha. But however, in the case of fine grains, because the size is very small compared to alpha dose, then we consider the contributions from alpha, beta, gamma from all radiations. So these are the parameters that we need to consider while calculating the dose rate. So according to this, we need to have these precautions on the field. First, sample should not be exposed to sunlight because the stored energy is very sensitive to light. And always sample from undisturbed or pristine deposits, so that we don't have contributions from other deposits. And also record depth, stratigraphy, and the latitude, longitude, because those will help to calculate the cosmic ray contribution. And as gamma has range of 30 centimeter, so we need to collect the sediment, surrounding sediment also, to consider the dose rate from all area. Yeah, so we talked about age. But now the question comes, what kind of ages we can find using luminescence or ESR dating? So here is the journey of crystal is shown in nature. So once the crystal is formed, and if it is buried, it will start to store energy. And if any event of exposure to light or heat happened, again its energy will be resetted to residual level. And if again it got buried, then it again will have energy stored. And if we collect sample at this stage, and in laboratory, we can calculate the energy stored in this crystal. So using luminescence and ESR dating, we only date the last resetting event. There can be multiple events of exposure, burial in the past, but we only date last resetting event. And if we collect sample here, like after the crystal formation, then we can talk about crystallization age, for example, for gypsum, carbonates, and volcanic ash. And if sample is resetted using heat, then we can date ceramics and wildfire event. If sample is resetted with light, then we can date aeolian, fluvial, marine, and glacial events using this burial dating method. Now, from last 1 decade, the new application of luminescence has also come, where we can date the exposed surfaces also. So the concept of exposure dating, it is mainly applicable on rocks. So once the rock is exposed to light means its signal will start to get reset. And as the time will progress, this resetting profile will penetrate deeper and deeper inside the rock. So if we have luminescence signal with the depth, then we can calculate the exposure time of this rock. And the advantage of this technique is that we can date multiple events of exposure and burial using this technique. So this is just a typical schematic shown here. So for example, if the rock is buried, and then we see, because it's buried, it's all the traps are filled. So we see a signal in saturation. Once it got exposed to sunlight, so near the surface, its signal will be near zero. Again, it got buried. If it's a signal will start to increase. Again, on next exposure near the surface, its signal will start to decrease. So with certain conditions, this technique can be applied, and this is more helpful for stone tools. It can tell about the whole history of stone tool, when it was used, it was in use or not in use. And these are the instruments for luminescence and ESR dating. So here this is a TL-OSL reader. Here we have irradiation source and different stimulation sources and photomultiplier tube. And here, if you on the here in this picture, you see that's how we put the sample inside the reader, the quartz grain or feldspar grains inside the reader. And this is the electron spin resonance system. We use X band, like the frequency with 9 gigahertz. And these are the tubes where we put the sample in the ESR. And these are the magnets that I talked about. And this is the microwave frequency generator. So we just put this tube inside the instrument, and we have information about the ESR spectrum. Now, talking about the applications of these methods, they have sorry many applications. For example, luminescence. For luminescence, for sediments, we can date fluvial, aeolian, glacial, and many others. And for rocks, we can date exposure events, burial events of the rocks, and hazards. And for temperature profiles also, it has application in thermochronometry. And in archaeology also, we can date potteries and stone tools using luminescence dating technique. And from the last 2 decades, its application to provenance, where we use mineral properties, has also been explored. So we can talk about sediment sources, transport distances using the luminescence properties of minerals. And in ESR detects free radicals, or we say paramagnetic centers. So it has application in biology, physiology, and food sciences, medicines, just to detect the free radicals, because these free radicals are very sensitive. So not sensitive, they are very reactive. So they will react very fast, and they will change the properties of the system. So just to detect, these ESR is used in biology and in food sciences. But I'll be mainly talking about its application in archaeology and geology. And now the range in which we can use this techniques, luminescence. Okay, it should be here 10. Yeah, luminescence can be applied from 10 years to 200,000 years. With some exceptions, it can go up to a million years. And these are the protocols that we use depending on the mineral we are using or the dating range we are interested in. So we have different protocols for luminescence dating. Similarly, for ESR, it can date up to from 1,000 years to 2 million years. And this is multi-center technique, where we can use different centers. For example, aluminum hot center we use, titanium, lithium, electron center we use for dating. And now coming to its application. So first for fluvial and marine terraces. So this is the example shown here for the floodplains. So these are the deposits during the floods. So whenever there will be a flood, it also brings with it sediments. And during its transport, that sediment is exposed to light, and that time its signal will be resetted. And after the deposit, it will start to acquire energy from the surrounding. And if we collect sample from these deposits, we can talk for the flood frequency and how the environment is changing, and it is affecting the landscape. And another application, if we date the terraces, these are the different terraces of the river. If we date these terraces, we can talk about the river evolution history, its in-season history, and the tectonic climate interaction from this kind of study. And this is one study from marine sediment is shown here. And similar here also, if we date these samples, we can have information about sea level change reconstruction and how the long-term coastal dynamics we can know from this kind of samples. And here mainly luminescence burial dating technique is used. Now another important application to date Loess Paleosol sequences. So these are the important archives for past climate through which we can have information about the climate oscillations. So you see on the left we have this section where we see different layers. There are some yellow layers, some brown layers. So the yellow layers, these are Loess deposits. These are mainly dust which form in the dry and cold climate, mainly in the glacial period, and the dark like brown layers, these are paleosols and mainly soil which form in the warm climate in the interglacial period. So if we have chronology from these events and by using the climatic proxies, we can talk about glacial and the interglacial periods and how the dynamics has changed in the past. And another application where we can date these glacial events using luminescence rock exposure dating. So if we have any exposed surface, it's glacially polished. Now it is exposed for a long time. So if we can date this using luminescence rock exposure dating. And similarly, we can date glacial deposits, moraines. These deposits will also help us to understand the glacial interglacial cycles occurred in the past. And now talking about aeolian sediments. Aeolian sediments, they mainly they tell us about the mainly if we talk about the dune formation, they tells about the dune movement, their stabilization, and how the desert landscape has evolved. So when the sand grains are traveling with wind, and during that time they are exposed to sunlight, so they have enough exposure to sunlight, and during that time their signal is resetted. And once they are deposited, they will start to acquire energy from surrounding. And here just one example shown from the aeolian deposit. If we date this, then we can talk about the patterns for dunes, their formation, their aridity history, about the past climate also we can talk about using other proxies related to climate. And will have chronology from the luminescence for these kind of deposits. And here we can use ESR burial because we have good exposure, and luminescence burial dating we can use to date this kind of deposits. Yeah, another application which is in tectonics and faults. So if there is any tectonic event happened, and in this crack during the tectonics, this rock got exposed to sunlight. Now it is exposed. So using luminescence exposure, rock exposure dating, we can estimate the time of this tectonic event occurred in the past. And similarly for faults, so during the faulting, because of the friction between the rocks, there will be production of heat, and depending upon the strength of the fault, the temperature can vary from 300 degrees Celsius to 1000 degrees Celsius, which are enough to erase the previous signals stored in the minerals. So it's we say there is removal of the signal from the mineral, and after the fault, it will again start to acquire the signal. So if we collect sample from here, we can talk about the fault activity history and about long-term seismic hazard assessments. Here also luminescence burial and exposure dating is used, and for faults ESR burial dating can be used. Yeah, another very interesting application in fulgurites. So these fulgurites mainly form in deserts. So in deserts, we know all the sand grains are exposed to light for sufficient time, and whenever there is a lightning event, and during lightning event, the temperature can go up to 1800 degrees Celsius to 30,000 degrees Celsius, very high temperatures. So with those high temperature, the quartz grains melts and they become glass, and they make this kind of structure. And during the formation of this structure, they can also trap some of the not melted quartz grains, like pure quartz grain. And if we can extract from this type of structure those quartz grain and date them, we can talk about the formation of these fulgurites, which tells us about the past lightning activity, and we can use luminescence burial dating. There will be challenges with the dose rate calculation. We need to consider the geometry and everything for the dose rate calculation for these kind of scenarios, but this can be done. Yeah. Now coming to application of luminescence and ESR in archaeology. So this is the sites. This is one of the study from my collaborator, Dr. Anil. Here different sites for human occupation in the past are shown, and we see in these sites we have stone tools. They are well preserved. So when in the ancient humans, they were using these stone tools, they were exposed to light. Once they left this land and the stone tools were there and any activity happened, these tools got buried, then they start to acquire energy from surrounding. And similarly, the deposited sand also will start to acquire energy. So there are two ways to date these kind of sites. One, you can date sediment. That sediment will tell since when those stone tools got when these stone tools got buried. And now with the advancement of technique, we can date these tools directly using rock luminescence burial dating technique. But because that technique is still in developmental stage, so we still have some issues with calibration in such kind of scenarios. Yeah, so and by dating these kind of sites, we have information about early human migration timings, and by analyzing the type of tools, it tells about the culture phase transition and about the dispersal routes. The chronology tells about the dispersal routes in the past by humans. And another application in archaeology, we can date pottery, because when pottery when we make pottery, the temperature goes around very high, 400 greater than 400 degrees Celsius, and that time the signal can be resetted from the pottery minerals in the pottery. And once the pottery got buried, it again started to accumulate charges. And by dating this, we can talk about the history of the pottery. And similarly, with the luminescence exposure exposure dating technique, we can date these monuments, which tells about the cultural and historical landscape evolution. And now with ESR dating technique, you can also date lime and mortars from this. This is the material between the bricks. So you can actually date these buildings and talk about their construction time periods. That helps to understand the past culture or architectural history. And here we can use luminescence burial and exposure for this type of monuments, and ESR dating for lime and mortar datings. Now, another very interesting application where mainly ESR dating can be applied to date the fossils. So here the example for tooth enamel is shown. So once any species died and it got buried, so the animals in the tooth, they store the energy. And if you extract this tooth enamel in the lab and do ESR spectroscopy, so you will see this kind of signal. And using the multiple aliquot additive dose protocol, you can calculate energy stored inside the these enamels, which will tell us about the when that species got buried. So ESR provides direct ages to the fossil remains, and hence it constrains the human evolution timelines. Yeah, now this was about dating application. Now coming to provenance. So provenance basically determines the origin and history of the sediments or rocks, which include their source area and transport history. So luminescence technique is very sensitive. So the quartz or the feldspar minerals, they have vast number of defects, and the luminescence is very sensitive to these defects. So if there will be any change in the defects, it will be reflected in the luminescence signal. On the left, there is one example shown here, where the OSL sensitivity, OSL is optical stimulator luminescence sensitivities, are shown for the samples from different regions, and y-axis here is log scale. So we see that there are differences in the luminescence sensitivities from different regions. So this tells that OSL sensitivity can be used as a provenance indicator for the sites. Here an example shown where we have three mountains. If they are formed from different magmas, they will have different defects. So their OSL sensitivity will be different because their defects are different. Okay, and if any river or fluvial deposit is coming from these three, it will have mixing of sediments from these three mountains. And if we collect sediment sample from here, it will be mixture from three, and we can if we take their optical stimulator luminescence sensitivities, and we can actually quantify from which mountain, how much contribution is coming from each mountain. So that's how luminescence is used for sediment budgeting. Yeah. And this OSL intensities can be used for sediment fingerprinting because every source has different OSL sensitivity or TL sensitivities. So in this direction that I am working now, so we are working in ERC funded project Progress, which was awarded to Professor Alida Temur. And in this project, we are trying to understand the changes occurring in the lattice defects of quartz during its journey in nature. So the aim of the project is to develop a quartz-based fingerprinting method for quantitative provenance studies to understand the tectonic and climatic processes. So in particularly, we are trying to understand why different sources have different sensitivities. Means what are the defects responsible for different sensitivities from different sources. And there are some studies which show that when a sand grain travels from its parent rock, in some sand grains there is increase in luminescence sensitivity, and in some grains there is no change in luminescence sensitivity. So we are trying to understand what are the parameters those are controlling this luminescence sensitivity in the rock samples. And another where we are working that in nature there are different geological scenarios, for example, metamorphism, volcanism. So how these different geological processes affects the crystal defects inside quartz mineral. And we are mainly interested in quartz because quartz is ubiquitous. It can be found anywhere, and it is well studied in luminescence community. Yeah, now the strengths and challenges that we have in these dating techniques. So luminescence dating technique, it uses ubiquitous minerals, quartz and feldspar. So those are present everywhere. So wherever you have suitable conditions, when you have good bleachability or you have this material present, you can date such settings. And these luminescence, for example, quartz has very good bleaching, so its signal will be resetted to very very low residual level. And these luminescence can be used to date very young samples of the order of like 10 years old sample can be dated using luminescence sensitivity. And yeah, middle age sediments can also be dated using luminescence dating. And it is good for it has been widely used for to date sediments and ceramics, means the events which are uh, resetted with light or with heat. And there are certain challenges also with luminescence dating technique, that its signal saturates early. It can date events up to 500 kilo year or less than that. But in some special cases, it can go up to like 1 million year. But mainly its applications are less than 500 kilo years. And in certain scenarios, for example, in fluvial settings, there are some partial bleaching cases. So we in that scenarios we need to correct for residual doses. Residual dose is just the amount of dose left after the exposure to light. And in some feldspars there are signal instability issues, which is known as anomalous fading. So we need to correct for anomalous fading in feldspars. And in some quartz, there are low sensitivity issues. For example, quartz mainly from Himalayas, they have very low sensitivity. So there are certain challenges in luminescence dating. Now about the strengths of ESR dating. This is multi-center dating technique, and it directly dates the trapped electrons, and this is non-destructive technique. Non-destructing means once you have ESR measurement on one sample or one ESR tube, you can remeasure that tube from the same protocol. And it has a higher range compared to luminescence. It can date up to 2 million years. And it is used for quartz and also tooth animals, carbonates, shells, and fossils. And it has application in archaeology. Yeah, here's spelling mistake. Sorry. Yeah, and there are certain challenges in this ESR dating also. There are some partial signal resetting issues in some scenarios. For this sample, for example, for aluminium holes, aluminium hole center, we have some bleaching issue. And there in some signals, there can be interference from other signals also. So we need to correct for those interferences using modeling or other methods. And dose rate uncertainties, it's there in both luminescence and ESR dating. So we need to be very careful during sampling. Just take sample from pristine deposit. There shouldn't be any interferences from other deposits. So if there are, we need to correct for dose rates for the other interferences. Yes, so in conclusion, luminescence it is widely used for sediments. ESR is used for fossils, caves, and it has application in older times also. But best results can be obtained if we combine ESR and luminescence approaches together. Yeah, and the take-home message of the talk is natural crystals, they store energy from nature, and luminescence and ESR dating techniques helps us to find the hidden clocks, which helps us to understand the Earth and human history, especially in the Quaternary period. Yeah, and just to brief, trap charge dating, it measures the last exposure time to light. So only last burial event we can date using these techniques, and luminescence is widely used for sediments, rocks, ceramics, and ESR for tooth enamel, quartz, and carbonates. So they have wide range of applications. They can be used for to understand landscape evolution, climate change, tectonic activities, and archaeology in Quaternary time period. And there are certain challenges also. So we need to understand signal stability, their bleaching conditions, environmental dose rates are essential for the reliable ages. And therefore, careful sampling and protocol selection is very careful to have a reliable ages. And future advances can combine luminescence and ESR with imaging modeling and with provenance tool. This will expand accuracy and open a new research applications. Yeah, these are some of the basic papers which you would like to go through for luminescence dating, for ESR dating. Yeah, thank you everyone for your kind attention. Questions are welcome.
Yeah, thanks, Monika, for that wonderful talk. Just fitting in our geomorphic talks, model methods, and more. So we try to focus on different methods. So thank you for taking through the methods, especially ESR dating. A lot of new things that's learned today. So yes, kindly unmute yourself if you have any questions. I see Professor Ashok Singhvi has joined us. So if you have anything to comment.
It was very nice to see Monika talk.
Thank you,
and
sir.
talk confidently. Compliments. And she has taken us through a whole range of applications. So compliments.
Yes, sir. It means a lot.
Yes, thank you, sir, for joining today.
Oh, it was an order from Monika that I cannot
No.
disobey.
Thank you for joining.
Yes, thank you, sir, for joining today. Yes, anyone having any questions, clarifications? Yeah, in case if there's none. Yes, sir, please.
Can I add a few statements?
Yes,
sure, sir.
I think one of the important contributions of luminescence dating has been to show that assumed sedimentation on the land is never continuous. The sediment deposition occurs only for a short intervals of time. The rest is periods of quiescence. And this is phase lagged with respect to climatic epoch. So it's not the glacial that we correlate lowest, but post-glacial. It's a few thousand years behind. And that is an interesting outcome of applications of luminescence to deserts, to loess, to any other deposits. So that our traditional land sea correlation events are not valid any further. Earlier, we used to correlate any sand with the glacial epoch or any loess with the glacial epoch. But if you look at the process-based interpretation of this, you have to create a sediment, you have to transport a sediment, you have to preserve a sediment, and this is the preserved sediment that you date. And this is and that is phase lagged with respect to the sediment creation itself and transport. So we are looking only at the preserved record. That should be kept in mind for any geological applications. Straightforward correlation with the ocean core or ice core records are no longer acceptable, especially in the last few 100,000 years. Thank you.
Thank you, sir.
Thank you, sir. Yeah, I just wanted to understand a little more on the provenance aspect of the luminescence. So, could you take us through like if we are getting different samples from like different part of say a river basin, so how we can understand that like from like how do we do that geo fingerprinting?
Okay, so you are saying if you have river basin samples, and if the if the sources like from where the sediments are originating, mainly the luminescence properties are characteristics of their origin from the rock, and every rock will have different luminescence sensitivity. And as they will as these grains travel, for example in rivers, in certain cases, their luminescence sensitivity increases with travel because they see different cycles of exposure to light. And there can be other mechanism also responsible which can increase their luminescence sensitivities in certain scenarios. So yeah, so their luminescence sensitivity increases with time, with the travel.
Okay. So
Can you
if
please
we
elaborate
imagine,
on? Can you please elaborate about river basin? Like what
yes,
kind of
river basin means a watershed. Like for example, if you take Ganga River Basin or Yamuna
Yeah,
River Basin, so from
yeah,
where the Yamuna River starts and it ends in Prayagraj, so
yeah,
till that the region that's in between defines a natural watershed. So that's
yeah,
called a river basin in
yeah,
normal geomorphologically.
yeah. Yeah, so generally we will see some trends in luminescence properties if we collect sample at certain distances in the
Mm-hmm.
travel. And if yeah, as I mentioned, in some cases it can increase, in some cases it can be constant. And if we see some abnormal behavior, it means there is some contributions from other catchments are also contributing. So it's
Okay.
idealistic to assume that they are coming from same source, but in natural scenarios, many other hill slope contributions can be there. So it's just a mixture of different samples from different origins.
Yeah. Yeah, I've seen very less amount of work in this, except few groups working in Brazil on Amazonia. Uh, there's some work in India as well, but yeah, like
Yeah,
there's
one
lot.
work is from Professor Singhvi's group.
Yes.
Yeah,
So yeah, there's there's lot to
for
know about this
Sabarmati.
provenance studies here.
Yeah, it's really interesting, and
Hmm.
yeah, it's people are still working on the
Yeah,
technical aspects also, and in the
yeah.
application
Because I've
also.
mainly seen ND and strontium fingerprinting
Yeah,
stuff, which people
yeah,
are doing.
yeah.
Very
Advantage
less
with
amount of
luminescence.
work is done in luminescence wise in this
Yeah,
field.
advantage with luminescence is that it has vast number of defects. So any small
Hmm.
change can be reflected in its luminescence properties.
Yes,
If
yes.
during the travel, if there is some other interferences, it can be
Hmm.
reflected in the OSL or TL properties.
Hmm. Yes, that's quite interesting. Yeah, yeah. Thanks, Monica.
Thank you.
Yeah. Anything more? Any questions?
Hi, Monica. It's Ayyappadas.
Hello, Ayyappa.
Yeah, I also have some same doubt regarding the provenance and also regarding the ESR dating.
Yeah.
So I from my sites I have some shell samples. So you told ESR dating is the minimum age that could be dated is 1,000 years, right?
Yeah.
So how does it work? Because is it the same we can't date less than 1,000 years, or the signal trapped would be more than 1,000 years, something like that?
Yeah, for younger samples, there is not much detectable signal in ESR. So that's why we have a bit higher. It starts from higher range.
Okay. That's same for all the type of samples, is that same for shells? Is that same for minerals? For all the samples, it's 1,000 years?
We can't say that. That is also dependent on the sensitivity of the sample. If sample is bright, we can observe signal.
Okay. And also is the charge trapping for ESR dating same as that for quartz, or for luminescence? Is it same as from the radioactive nuclides?
Yeah.
Yeah, okay.
Yeah, they are dating same. Same trapped charges. In luminescence, it's the emission from electron and hole recombination, and ESR, you are dating either trapped holes or trapped electrons. But they are dating same process.
Yeah, okay. And also regarding the provenance, is it by the transport mechanism the signal changes, the signals from the sediments changes, or it's mainly from the provenance of the sediments, if it's a different form or of origin for the sample, if it's from a metamorphic terrain or if it's from igneous terrain?
Yeah, actually, that's very good question. So there are studies which shows that it increases with travel. And that's what we are trying to understand in our project. What are the reasons? Either these are some inherited defects inside the quartz minerals which control the sensitivity of the quartz samples, or is it the other factors, for example, weathering, or which controls this provenance or increase in sensitivity in nature? So we are still trying what are the reasons for that. These are observations that they change.
Yeah. Okay. I have like the same doubt with the provenance. Like my samples, they are from a single provenance. I could say like it's from South India, and it's from mostly from the Darwa Craton, and it's mostly like the stable Darwa Craton region.
Okay.
So mostly metabolites or granulates. But still within the same disk, I would say we could have like different yields from different grains, right?
Yeah.
So how can we like differentiate the yield of the samples and from the provenance studies for the provenance studies?
Yeah, so yeah, this is also observation that if we are dating 100 grains, out of 100 grains, only you say 4 or 5 grains are giving signal.
Yeah.
So that's also observation. So the reason we need to understand what are the defects responsible for this kind of change.
Okay, yeah.
So for luminescence, that's some people also use single grain because we have some variability in the grains, as you mentioned. Some grains give signal, some not. So some people use single grains. But in cumulative also, if we, for example, if we have two different sources, in cumulative liquid also, we will see some differences in their signals.
Okay, yeah, thank you.
Yeah, but most, I think most applicable will be single grain. See.
Thank
But
you.
yeah, these are open
I
questions
think,
to understand
just
what are
also
the
to
reasons
add,
for that.
yeah, there even in my samples. So like the luminescent thing varies, like sensitivity varies across grain sizes. So as I switch towards a lower grain size, things are a little bit better compared to higher grain sizes. Like if I switch towards a grain size around 125 to 150 micrometer, so things becomes brighter compared to a grain size which is like 180 to 212. So yeah, things are different in different grain sizes as well. So yeah, I think the physical property wise things are also
Yeah, that's
to be taken
interesting
into consideration.
observation.
Yeah. So maybe, yeah, future project needs to be done.
Yeah, these are open questions.
Yes. Yeah, so anyone else, anything, any more questions? Okay, I think, yeah, pretty much things are done from our side, maybe. So yeah, thank you everyone who have joined today, and thanks Monika again for giving us this wonderful talk. And yeah, and we would love to hear some session soon again on luminescence from you again. And yeah, next month we are going to schedule another talk. Details would be coming up soon on different social media posts and mailing lists from where we have got today's information. Yeah, thank you everyone for joining today, and yeah, have a nice day.
Thank you everyone for joining. Thank you, Jayesh.
Yeah, thank you.
It was a wonderful